And welcome back, everybody. So, we last time finished up the material in chapter 4. That was the chapter on orthogonality and not least squares, on Graham-Schmidt in particular, QR factorizations. We ended on an application with the Fredholm alternative and talking about orthogonal complements and how that related to the 4 fundamental subspaces of a matrix. And we are now going to kind of readdress one of the questions that we answered at the end of that section, which was if this equation here, if ax equals b doesn't have a solution, or maybe it does have a solution, what is the best solution for it? So specifically, this is the case where the kernel of this matrix is non-trivial, and we have infinitely many solutions to the system, but we would like there to be, in an algorithmic or practical sense, exactly one solution to that equation, regardless of if there are infinitely many or not. So, why then did we say that the best solution was the solution x with the smallest norm? And specifically, that was with respect to the 2 norm. So why would that be? Why should smallest mean best? And the answer that we're going to take here is going to come from a little bit of context. So I actually have 3 different scenarios, 3 different settings that might justify why that is our measure of best, why the length of the solution vector should be a measure of best. And first application, actually all of these applications have to do with the fact that we are trying to minimize something, right? And first application might be familiar to those who've taken any physics or any dynamical systems theory. We would have a potential energy associated with some system, and that's going to give us kind of a measure of where energy wants to flow in the system, where particles want to move. And specifically, the net force that we would get off of the system is going to point in the negative gradient direction of that function v. So, or at least in many different scenarios, that's going to be the case. It's one of the simplest ways for us to measure where things flow. Right, and remember the gradient is going to be pointing in the direction of steepest increase in that function v. So in effect, we are actually pointing our particles downhill. So they want to lose potential energy as they move through the system, or as they move through whatever space they're in. So in this sense, the potential function is going to determine the acceleration of whatever particle we're dealing with. And specifically, when the gradient is 0 at a specific location, there is no acceleration. And the system is in mechanical equilibrium, right? The acceleration is 0. So it's not that the velocity is 0, it's just that the velocity isn't changing, right? So there's we are stuck in one inertial reference frame for that system, right? We are not accelerating. So in this instance, v of x star down here, so let me go ahead and get back to my pencil, right? V of x star is what's called a critical value for the system, right? If you've taken multivariable calculus, you know this. And x star is referred to as a critical point for the system. And in particular, if that critical value is a local minimum for the system, kind of like it is over here in the diagram, then x star is going to be called a stable equilibrium, right? This is right. If I can't move out of that well while going downhill is what that means, right? Compare that against the top here. Any direction I move is technically going to be downhill, and there are some directions on this little hill that are going to move uphill, and others that still can move downhill. So the x's in this diagram are corresponding to critical points or equilibria that are not stable or unstable. All right, but the point is, that we would like to find all the stable equilibria for a system with a given potential function. And one way that we can do this, well, is exactly what we've outlined upstairs. We're just trying to flow downhill until we can't anymore. So we are trying to minimize that potential function. All right. Second application. If I have a general system of equations, right, these don't have to be linear sets of equations. I just have a collection of equations, all of which I can set to 0. Right? If I have any constant terms, I can throw over to the left-hand side and force a 0 on the right. If these equations or these functions on the left-hand side are polynomials, we are now within the realm of a field of math called algebraic geometry. Right, and this is going to be an ideal, like the points that this creates are going to construct something called a variety. And we can study them using ideals of functions. But let's not get too carried away here. We would like to solve this general system of equations for whatever solutions there might be, if any. So what I'd like to do is consider the following function, which is going to be just the square norm, right? The square 2 norm of the vector on the left-hand side, right? Then if we were to determine where p of x is equal to 0, then that would mean, right, by the fact that this is that we're using a norm, a bona fide norm, that if I hit the 0 vector here, that means I have definitely minimized this function, and in fact, I have solved the original system of equations upstairs. So in other words, I would like to minimize p of x. Okay, so again, in solving this equation, we're going to have to minimize something. And as per usual, right, we have our linear system of equations, ax equals b. And we would like to kind of riff on this notion from upstairs that we want to create a function p to minimize. And something that we can do toward that end is just to move all these b vector components over to the right, over to the other side. And we'll be in the same setup as before, right? But all the functions are now going to be linear functions. And I would like to minimize this guy. And the system will only have a solution if I can get this to 0, if I can get the p function to 0. This is not always the case, right? We might not be able to solve these equations, right? So we would like to get as close to a solution as we can. And that's exactly what we were solving at the end of chapter 4. It's like, how can we make this residual function as small as possible, or the residual vector as small as possible, right? And that would be, in framing this in terms of a minimization problem, we're trying to minimize this p function, right? The square norm function. So generally, you might have guessed it, these are called least squares solutions, right? These are the guys that make the square norm smallest between where it can go and where it needs to go, right? So we are trying to find some element in the image of this matrix that is closest in square norm to the solution vector b. So even local minimizers are usually pretty close to the image. So we always have some global minimum, but it may not be exactly at 0. And it's very, very important to remark here that I was using the 2 norm here, and this is going to correspond to squares. But what we would like to really distinguish here is that the minimization problem fundamentally changes if we change the norm or the inner product that we're using on our vector space. So we need to be very careful to make it very, we need to be very clear about what the norm is, and from the get-go, and say, okay, we're using an inner product space, or we're using just a normed linear space. This is going to be very tricky to deal with in arbitrary spaces. But we really want to use inner products rather than our arbitrary norms, and you might have guessed this is due to orthogonality, right? We want to invoke orthogonality to try to minimize these guys. We'll see how to do that in the next video. But the third application here, similar to the previous, is that we would like to figure out the points that are closest to certain sets. And you may or may not remember this from calculus, where we would have some function, say the exponential, and some point not on that curve, and we wanted to figure out what is the closest that this curve gets to that point. Well, that's the same problem that we're trying to answer here. Right, we are trying to figure out where these functions, how close these functions are able to get to certain points, or what the image is able to do. So we're trying to solve something like this equation. F of x is equal to c, and well, let's just say that this has no solution, so that there's no way for me to, so coming back up to this example, we're not dealing with the case where the point is on the curve. No. We are moving this guy off of the curve and asking, okay, where is it closest to that curve? So instead of finding solutions where, well, instead of trying to find where the solution meets the curve, well, it doesn't, we're going to try to minimize a square norm again, right? And we interpret this geometrically as saying that f of x is closest to c when that p function is minimized. And in the case where the vectors x are restricted, right, this is actually really important to us, where our input values are restricted. So coming back to this picture, maybe we have the entire exponential curve and we have a point over here. So we'd like to be able to say that this is the shortest distance, but let's say that we're only allowed to use values that go up to a certain, or outputs that come from a certain input set. So we're only allowed to use x's that are up to 0, say. Then this is no longer the shortest distance, but rather this straight line distance is. So we have to be we have to reframe the question, or reframe how we're going to solve the problem, when we restrict the values from our input set. And this looks very close to the Fredholm alternative, where we're saying, okay, we need to make sure that we can only use vectors, or we can only solve the system when vectors belong to the orthogonal complement of the co-kernel of a matrix. Right, same idea. Let's push the vectors outside of the co-kernel and see what happens. So the problem would be to find all the points in a certain subset where the image is closest to this vector c. And again, we are minimizing something. And this sort of setup is called a constrained optimization problem. Right, so this is where we're heading for the next section. We want to figure out the solutions to all of these problems, and we'll frame them in terms of minimizations, or optimization in general, right? So in order to see where we're going to start, go ahead and check out the next video, and I'll